Hello students, I am Dr. Alka Kumari, Assistant Professor, Department of Mathematics, Patna Women's College, Patna University. So in this lecture, I am going to talk about real analysis in context to a sequence. So let us know what is real analysis. So real analysis is a branch of mathematics which deals with the properties of real numbers, their convergence, their continuity and many more properties. So coming on to sequence, how we are going to define a sequence. So talking about sequence, we can define a sequence to be any function from n to x. That is a function whose domain is going to be the set of natural numbers. So any function from n to x will always going to define a sequence, and it is generally denoted by the symbol sequence xn or an or bn, where xn is called the nth term of the sequence. Since here we are concerned about real sequences, so here I am going to define what do we mean by a real sequence. So any function from n to r will always define a real sequence, or we can call it a sequence of real numbers. Now how a sequence is represented. So here you can see that there are some examples. So here you can see that the nth term of the sequence is written to be, in the first example it is written as 1 by n. So corresponding to n is equal to 1, we have first term of the sequence is 1, second term of the sequence is 1 by 2, third term of the sequence is 1 by 3. In this form we can write in terms of the sequence in an array of numbers. So you can see examples 1 by n, n by n plus 1, 1 by 2 to the power n, 2n minus 1, minus 1 to the power n. Now how a sequence can be represented graphically. So if we are going to talk about graphical representation, here you can see that corresponding to n is equal to 1, the first term of the sequence is 2. Corresponding to n is equal to 2, the second term of the sequence is 4. Corresponding to n is equal to 3, the corresponding term of the sequence is 8. So in ordered pair, we have arranged the terms of the sequence correspondingly. Okay, so in this way we can represent a sequence graphically. So this is graphical representation of a sequence. Now coming on to limit of a sequence. So informally speaking, how we can define the limit of a sequence. The limit of sequence an is intended to describe how an is going to behave as n it tends to infinity. To be more specific, we can say that a sequence an is said to tend to a limit L if the terms of the sequence eventually becomes closer and closer to L. So how we can define limit of a sequence? So graphically you can see that here we have sequence n is equal to 1 by n, and we know that limit of the sequence is 0, and this is an example of a convergent sequence. So here you can see that all the terms of the sequence are in monotonic decreasing manner, and they are approaching approximately equal to 0. So now we are able to define a convergent sequence. So in a simple language we can say that a sequence is convergent if and only if its limit exists finitely. That is, a sequence an is going to converge to L if for a given epsilon greater than 0 there exists a positive integer n naught such that mod of an minus a is less than epsilon for all n greater than or equal to n naught. Now let us define some more type of sequences. So coming on to a bounded sequence. Suppose there is a sequence is given and we have to define a bounded above sequence, bounded below sequence, a bounded sequence. So here how we are going to define a bounded above sequence. Suppose there is given an array of sequence of numbers and we are going to find a positive number such that all the terms of the sequence are going to be less than that number. Then in that case we can say that sequence is bounded above, and if all the terms of the sequence are going to be greater than some positive number, then in that case we can say that sequence is bounded below. So in another way we can define a bounded sequence. If a sequence is bounded above as well as bounded below, a sequence is going to be a bounded sequence. Now another type is divergent sequence. how where we have till now we have defined what do we mean by a convergent sequence, what is a bounded sequence. Now what do we mean by a divergent sequence? So basically we can say that if a sequence properly diverges to either plus infinity or minus infinity, then in both the cases we can say that sequence is going to be divergent. Now there arises when we say that sequence is going to diverge to plus infinity and when we are going to say that sequence is going to diverge to minus infinity. So a formal definition or mathematically we can say that a sequence an is said to diverge to infinity if given any real number k, however large, exists such that an is greater than k. Then we say that limit of an is as n tending to infinity is infinity. Similarly, a sequence is diverges to infinity if there exists a positive number k such that an is less than minus k. So, for example, the sequence n and n square diverges to infinity, the sequence minus n and minus n square diverges to plus infinity. Now coming on to oscillatory sequences. So as you know, what does oscillation mean? You have seen a pendulum oscillating finitely within a finite limit. So how we are going to define oscillatory? If a sequence is oscillating within a finite limit, we can say that the sequence is oscillating finitely, and if a sequence is oscillating infinitely, that the limit ranges between minus infinity to infinity, then we say that sequence is oscillating infinitely. Then monotonic sequences. So how we can define monotonic sequences? So monotonic means either monotonic increasing or monotonic decreasing. If we have to find out that either sequence is monotonic increasing or monotonic decreasing, we have to simply calculate a n plus 1 minus a n. If it is greater than 0, sequence is going to be monotonic increasing, and if it is less than 0, it is going to be monotonic decreasing. So it's very easy to find out whether sequence is going to be monotonic increasing or monotonic decreasing. Now, till now we have studied that how we are going to show that the sequence is convergent, divergent, oscillatory, monotonic or bounded. If we have to show that somewhere we face some problem in calculating the limit of a sequence, there to calculate the limit we can use limit theorems like this. So limit theorems, you can use squeeze principle to calculate the limit, you can use Cauchy first theorem of limit to calculate the limit, you can use Cauchy's second theorem on limit to calculate the limit, and from here you can make sure that either sequence is going to be convergent, divergent or oscillatory. Next method, we can use monotone convergence theorem to check the convergence of a monotonic sequences. So monotone convergence theorem says that a monotone sequence of real number is convergent if and only if it is bounded. In another way, we can say that if a sequence is monotone increasing and bounded above, it will be convergent, and it will converge to its least upper bound of the set formed by the terms of the sequence. And if a sequence is monotonic decreasing, it is going to be and bounded below, it is going to be convergent, and it will converge to the greatest lower bound of the set formed by the terms of the sequence. So we have studied monotone sequences. So if we are able to identify that a sequence is monotone, there we can apply monotone convergence theorem to check the convergence divergence of the series. Remember that a monotonic sequence can either diverge or converge. A monotone sequence can never oscillate. So remember this fact. So here are some application of limit theorems, monotone. Suppose you are unable to calculate limit easily, then here you can see one example that we have used Cauchy's second theorem on limit, and here one example we have used monotone convergence theorem to check the convergence of the sequence. In another example, you are seeing that squeeze theorem has been applied to the problem to find out the convergence of the sequence. So till now we have learnt notion of limit, monotone convergence theorem, how we are going to find out limit to check whether sequence is convergent, divergent or oscillatory. Now there a monotone convergence theorem has one drawback. What is the drawback? That monotone convergence theorem can be applied only to monotone sequences. It is limited. Okay, so we need here one more criteria that we can apply to any arbitrary sequence. For that we are having Cauchy's general principle of convergence of a sequence. So first of all we need to know what is a Cauchy sequence. So a sequence UN is a Cauchy sequence if for a pre-assigned positive epsilon there exists a natural number k such that mod of UN minus um is less than epsilon for all mn greater than or equal to k. So in this way we can define a Cauchy sequence. Now Cauchy's general, what does Cauchy's general principle states? So Cauchy's general principle states that a sequence is going to be convergent if and only if it is a Cauchy sequence. So if we are going to identify that whether a sequence is a Cauchy sequence or not, we can easily say that if a sequence is a Cauchy sequence, it is going to be convergent, and if a sequence is not a Cauchy sequence, it is going to be divergent. So Cauchy sequence generally applies only to the nth term of the sequence. So if we are able to identify the nth term of the sequence, we can easily use Cauchy's general principle of convergence of a sequence. So in this way, in this lecture we have talked about limit, notion of limit, convergence sequence, monotone convergence theorem, Cauchy's general principle, and how on problems we are going to apply that and where we are going to apply that. So I hope students will find this lecture useful to you. Thank you.